Okay, so what you're going to see on your screen today is us investigating, and we're going to go through and we're going to build what the graph of our sine function looks like. So you'll notice our function's labeled f of x, and it's equal to sine x. And so what we're basically going to do is go back to grade 9 in a way and say, let's build what this function looks like using a table of values. So at the top of the screen, you'll see our basic definition for what sine is, opposite over hypotenuse. But then to the right, we can also take a look at that from the standpoint of a rotation angle. And so you'll notice that point P just happens to be some point that lies on a terminal arm. And so we've given it very generic coordinates, x, y. And if we were to go through and say, well, how could we talk about the dimensions of the triangle formed? You'll notice that for us to get to point P, we would go across x units and up y units. Now, if we were to rotate point P and keep moving it to different locations on that arc, then you'll notice that point P would form a circle. And so quite often we'll refer to the hypotenuse as r because that would represent a property of the radius of the circle. And sometimes you may see what's referred to as XYR definitions, and therefore my opposite side could be my y coordinate and my hypotenuse my r. And so that's why you'll also see sine referred to as y over r from time to time. Okay, what I'd like to do is I'd like to go through and I'd like to now fill in this big table. Now, all that is a table of values for us, but we've kind of rotated it and turned it sideways. You'll notice that all we're going to focus in on are all of our multiples of 30 degrees. So, what we're going to do then is we're going to figure out what is the value of sine x for each of these given x values. And so we can go through and we can make a substitution of 0. We should all be okay to be able to evaluate what the sine of 0 is. Sine is my opposite side, and if I rotated nothing, then I have no opposite side, 0. I could then continue along, coming up with the exact value of each of those sine ratios. Now, down below that big table, just if it helps, you can go through and you can deal with each of these as a rotation angle. So maybe that's my 30 degrees. We should all be good to be able to determine the value of sine 30. We should know that without a calculator and probably without even drawing the special triangle anymore. But that is our 1 root 3 and 2, and therefore my sine value is opposite over hypotenuse. Okay, so those next angles, perhaps we might use that to help us out on a 60-degree angle. I don't think we need a 91 as we're going vertical, but perhaps this one becomes our 120. You feel free to use those diagrams. I'm going to challenge you to try not to draw the picture, and instead try to imagine, try to view in your head what each of those rotation angles would look like. I'd like you to go through now, pause the video, and fill in the rest of that exact value of sine x for each of those angle values. Okay, pause the video now. Okay, so we're back. And so maybe we went through and we drew our triangle and we're good on our 60 being a root 3, 1, 2. And therefore our sine of 60 is root 3 over 2. We should be good that if I examine the sine of 90, my terminal arm is vertical, which means I have no adjacent side, so everything is opposite. When I then examine my sine of 120, I can drop in. My related acute angle would then be 60 degrees, and so therefore I have my root 3, 1, and 2. That is a very messy root 3. My sine of 150 we should have found to be 1/2. My sine of 180, when I'm directly left, I have no opposite side. My sine of 210 would give me a 1/2, but because I'm going down, I'm now negative. I would have a negative root 3 over 2, and we should be able to then confirm the rest of those values. So hopefully we went through and we matched up. All I'd like you to do now is take out your calculator and let's get some decimal approximates for those. So for us to be able to go through, we should be good that all of these values I would not need a calculator for. That the only thing that I need to come up with an approximate for is my root 3 over 2. So go ahead and push some buttons, get that value. And so we should have found then that we get approximately 0.87, that being negative, and that ends up being our table of values. So now that we have that table completed, what I'd like to do is just slide down to the bottom of that page where you see that set of axes that's been given. And I'd like you to take that table of values and I'd like you to plot all of the points that we found. So pause the video now. Let's plot all of those points on the given table. Okay, we're back. And so to be able to go through, we should have a point at 0, 0. We then had a point of 30 degrees, which if I look on my scale on my x-axis would be each grid line. So that would put me up at about a half. 60 degrees put me at about 0.87, so almost halfway in between. 90 degrees put me at 1. And as I start to then plot all of those points, I should start to see all of those red dots on my graph. So if we're good to get all of those points, then what I'd like to do is just follow that last instruction that says, let's join the points with a smooth, continuous curve. And so if I was to connect all those points the best I can with a smooth, continuous curve, I should get something like that. What we now have on our grid is what's referred to as our sine curve. There is the graph of our sine function, our sine ratio, for any given angle. Okay, let's jump in a little deeper to examine some of the properties and the nature of that curve. Okay, so what we're going to do is we're going to kind of take a step out of the note for a second, and it might help some of us to see how that sine curve gets generated by a little more than a table of values. We should be good that we can build that graph through each of those points, but we also want to kind of break down a little bit, and maybe it might be a little bit more useful to see it get developed over time. So what we're going to see on the screen is an animation of us rotating around our terminal arm. So you'll notice that as we move, what we are measuring is the length of the red line. It is the length of the opposite side of every one of those special triangles. So as we start to rotate, and as I start to now increase, we can see what happens when we get to 90 degrees. We then had a value of 1, and then as we slowly work our way down, we get back to 180 where we have no opposite side. And then we can continue and so on. The length of that opposite side then becomes negative. And as it becomes negative, we see our graph drop below 0. So I'm just going to hit play on this so that we can see that curve repeatedly get developed. And so if we were to now rotate, we should be able to see that sine curve get developed. And so Stay on this for as long as you need to. Replay and rewatch the way that on the left side, our circle, our terminal arm, is rotated around the axes, and how it has then a matching length of the opposite side graph being plotted for each angle. So, as I said, rewind it, stop it, watch it, see as much as you can to just help you see how that graph gets developed over time. And so what I'd like to do is then just hop back onto that first page of our note, because I'd like to break down a little more the basics of that curve. So as we examine that, I want us to notice that we should be able to take that sine curve and break it up into quarters. What I mean by that is, from 0 up until 90 degrees, that was my terminal arm lying in the first quadrant. And so if I was just to put a little wavy line down, then everything that happens between that exists in quadrant 1. And so we'll notice that our sine curve starts at 0 and then rises up to hit its peak at 1. Once we then cross over and we enter into quadrant 2, you'll notice that your graph starts to fall in value. As it falls, we get back to 0 at the end of quadrant 2 at 180 degrees. Our graph then drops below the axis, so therefore it becomes a negative, and it stays negative and keeps falling all the way until we get to the end of quadrant 3. And now, once our terminal arm passes 270 degrees, our graph begins to rise again, and it will keep rising until we finish off that first rotation, the end of quadrant 4. So if we can start to look at our sine curve as basically quarters, we begin at 0 and we rise, and we keep rising until we get to the end. We then fall, and we keep falling to 0 until the end of quadrant 2. We then fall all the way to the end of quadrant 3, and we rise to the end of quadrant 4. If we can work our way through, and keep in mind that that sine curve is always broken up into quarters because it's based on rotation angles, that's really going to help us as we get to working more in depth with our sine curve. So let's now take a look at the second page of that lesson note. What we're going to do is we're going to just talk about some key features of our graph. So we're going to very quickly go down and just nail out all the key features of our sine curve. So what was the maximum value of sine x? Sine x got to the very top of its graph, had a maximum value of 1. For what value did that maximum value occur? Well, we notice that that occurred at an x value of 90 degrees. What was the minimum value? So what's the very bottom of my sine curve? We got all the way down to a value of -1. And when does that occur? At an angle value of 270 degrees. If my graph goes all the way up to 1 and all the way down to -1, then it has a height of 2 units. When we then need to find the amplitude, we know that the amplitude is half the height. That gives us a value of 1. So we're going to want to know those key values off by heart as we start to work our way through. So let's take a look at number 4. We now need to make a conjecture. So our conjecture is a hypothesis, an educated guess. So make a conjecture about the appearance of what y equals sine x would look like for this domain. And so we notice that our domain starts at 0, and therefore I know that my sine curve also starts at 0. What does my sine curve do? It rotates and hits its maximum at 90, comes back to 0, hits its minimum at 270, comes back to 0. However, my restriction then says I have to go all the way up to and including 720 degrees. That tells me that I have 2 full rotations. So my sine curve is going to repeat again. Because my rotation angle can keep turning, that terminal arm can keep rotating, we may be able to see why a sine curve starts to fit into a periodic function. So what is our conjecture? Our conjecture is that it is periodic. What do we then have? We have 2 cycles. So I think everybody should then be able to go through and make a conjecture about what the graph would look like for the domain in problem 5. Now we're going all the way to negative 360 and up to 720. Okay, so we know that we then have start at 0 and rise and hit our peak and come back. I need the other rotation in that direction. But now since we're going backwards to negative 360, my curve would then continue all the way back. What do we know in that case then? Since it is periodic, that means we're going to have 3 cycles for that graph. So a graph with no restriction on it would go forever and ever and ever in all directions. Take a look at problem 6. We're going to use our conjecture now to graph the domain negative 360 to 720. So what we want to get to is the point where we know our sine curve off by heart. Similar to what we did in Unit 4, where we started to transform all of these graphs, we're going to do the same thing to our sine curve. So we want to be able to get down the basic components of what our sine curve looks like. This would be my suggestion to you. That at the very least, we know when our graph is at 0, is at its max, is at its min. So if I was to just graph in red my first positive rotation of my sine curve, I know my sine curve starts in the middle and now it rises. I know that it's going to rise and hit its peak at the end of the first quadrant, which is going to put me, at 90 degrees and my maximum value of 1. My sine curve is then going to fall and get back to 0 at 180. My sine curve is then going to continue to fall until it gets to its minimum value at 270, and it returns back to 0 at 360. Now, some of us may be able to connect that with a smooth curve, knowing what we know about our sine curve, and create a pretty decent graph. Others, we might struggle on it. And so, my recommendation to you is put in all of your half values. So, we know that at 30 degrees, our sine value is a half. And if that curve was then to continue, I know that at 150, it would be a half. As we cross the x-axis, I'd also know that at 210, I would be at negative 1/2. And as I continue and rotate back up, at 330, I would be negative 1/2. And if I was to include those half values, now I should be able to connect those curves using a pretty decent curvature. So if I was to connect that in gold, and I'm just going to keep that so that we can see all those values, those original points, then my curve is going to start to decrease, and it's going to curve down. And as soon as I cross that x-axis, my curve starts to curve up. I make a nice smooth curve. I didn't quite get to the bottom. Make a nice smooth curve, not a V, it's not pointed. And there we go. So there would be my first positive rotation, 0 to 360. I think if we can see that basic shape, then we should get really good at only using the maximums, the zeros, and the minimums to create our picture. So what we can do then is go through the next rotation. So I know then that my next rotation is going to occur 90 degrees ahead of that. There's my maximum. My next key value is going to get hit 90 degrees after that. My next key value is going to get hit 90 degrees after that. And my next key value, 90 degrees. I know that I can break my curve up into its quarters. What I want you to do is I want you to try connecting that with a smooth curve and see if we can avoid having to plot our halves. So if I was then to connect that, smooth curve, now that I cross, I start curving up, smooth curve. Hopefully you notice that your second positive rotation doesn't look that much different than your first one, but you didn't have to plot all those extra points in between. So what I'd like you to do then is I'd like you to go and now plot your maximums, your zero, and your minimums back to negative 360 degrees and see if we can construct a pretty decent looking curve. So pause the video now and we'll see if we match up. Okay, we're back. So I should be good to be able to plot my next key value at a minimum 90 degrees back. My then zero is at my next 90 degrees back. Again, I'm hitting all my quadrants. I'm landing on each axis. 90 degrees before that, I would have to be at my maximum. And 90 degrees before that, back at zero. If I was to then just connect those with the smooth, I got a little rounded there. But even if you take a look at it, we get a little rough in some spots. We still have a pretty decent curve. So just as a little bit of a check so you can see how close I was to those points. If I was to go back 30 degrees, I should have a point at a half. That is almost perfect. Back 30 at my zero. If I was 30 degrees to the right of 180, I'm a little bit off there. If I was 30 degrees behind that, I'm a little off there. If I was 30 degrees before 360, considerably off. And that's where I say I was rounded. But really, if you took a look at that picture, that's still pretty decent for us to get a good idea of what our sine curve looks like. So as you're dealing with your sine curve, let's work with our maxes, our zeros, and our mins to try to create that graph. Last thing what we want to do is we want to knock out some key properties on the bottom. Question 7, is the graph of sine x periodic? We've already answered that. Clearly, yes. If so, what is the period of 360? And if we recall from our last lesson, period is how long does it take for that curve to repeat. We notice that that curve repeats every 360 degrees. So our period for our sine graph is 360. How can you verify that sine x is a function? Well, we notice that that sine curve would pass the vertical line test. Now, you don't need to use the vertical line test for it. You can use the definition of a function for it. But notice that every single x value has one and only one y value. Therefore, it would pass the vertical line test. For the function, sine x, what is the domain? We should be good that you could sub any value in for that angle because our terminal arm could rotate and rotate and rotate forever and ever and ever in either direction. What is the range of that function? Very important. We notice that our y value is greater than or equal to -1 or less than or equal to 1. Or if we wanted to use alternate notation, all the way from -1 to 1 inclusive. So there's some key features of our sine curve. Hopefully we're good with developing that and being able to recognize some key features from it. Okay, so as we take a look at the screen, what you'll notice is we're going to go through and we're going to address the exact same thing now, that same process, but we're going to address our cos function. So if we were to kind of jump in and deal with a very similar process as what we did before, we know that cos is our adjacent over hypotenuse. And if we were to look at that then as XYR definitions, our adjacent side is always across, which is our x value, and our hypotenuse would be the radius of the circle, and therefore r. So what we're really examining then is what is happening to the adjacent side, or the x value. So what I'm going to do is I would like you to be able to go through and complete that table. We should be good to complete that table on our own right now. So I want you to pause the video, work your way through, complete that table, and we'll see if we match up. Okay, hopefully we see we've got the correct table on the screen. Everything matches up with what you have down. And if they do match up, then we should be pretty good to be able to go through and deal with plotting. So on the set of axes that you have at the bottom of that page, we're going to work our way through a pretty consistent scale. It's not our ID scale, but one that was similar to what we just dealt with, which means that we're going to make every grid line on our y-axis worth 0.2, which then makes 1, 2, 3, 4, 5 lines down to -1. And each scale line or grid line on our x-axis is going to be worth 30 degrees. So 1, 2, 3 gets us to 90 degrees, another 3 gets us to 180, another 3 gets us to 270, and then that finishes our positive rotation at 360. So what I'd like you to do then, plot all those points, see if we match up. Okay, pause the video now. And so hopefully we match up with the points that we have. And now I'm going to go through and I'm going to connect those with a smooth curve. And so as I connect them, I know that I'm going to fall down to here, come around, and now increase up to here. And so hopefully we have something that looks like that. What I would like to do is I'd like to go through and break this down the same way we broke down our sine curve. That we notice that everything up to 90 degrees would be our quadrant 1. So if we recall that what we're talking about when we say our cos is we're talking about what's happening to the adjacent side or to our x values, then we should be good that at an angle value of 0, our terminal arm is directly across the positive x-axis. There is no opposite side. There is no height, which means that our adjacent side, our x value, is everything. And everything as a value puts us at 1. Now as my terminal arm starts to rotate, my adjacent side starts to become shorter and shorter and shorter. I eventually get to having no adjacent side when my terminal arm is completely vertical. That happens at our 90 degrees. As soon as we cross 90 degrees with our terminal arm, then the only thing that happens is our adjacent side starts to become longer, but since we're going to the left, it becomes a negative value. And we go all the way until we get down to 180 degrees. At the end of quadrant 2, our terminal arm is as long as it can be for x values. It's completely sideways. As soon as we cross 180 degrees, my adjacent side, my x value, starts to become less and less and less. And it's going to keep becoming less until it becomes 0. And the next time that I have no adjacent side is when my terminal arm is completely vertical. That's going to happen at 270 degrees. I am on my negative y-axis. As soon as I cross my negative y-axis, then I'm going to start to have an adjacent side again. And it's going to keep getting longer and longer and longer until we get back to our start. And that finishes us off within quadrant 4. So if we can break down our cos graph the same way, we should be good. Notice that my maximum to my 0 to my minimum to my 0 to my maximum occurs at my axis values the same way as what my sine curve did. They're just different values. So if I was then to follow the instruction at the bottom of the page that just says continue the graph now back to negative 360, we should be able to pretty quickly say 90 degrees before 0, negative 90, I'm going to get back to 0. 90 degrees before that, I'm going to hit my bottom at negative 1. 90 degrees before that, I'm going to hit back at 0. And 90 degrees before that, I hit back at my max. If I was to go through then and connect those with the same smooth curve, now I'm curving up all the way until I get back to my maximum at 1. So hopefully we're able to construct that cos graph in a very similar way as what we did in our sine curve. Now what I want to do is just break down some key components to our cos graph. So let's go through and let's answer some of those problems at the top. Okay, what was our maximum, or what is the maximum value of cos x? We noticed that cos x hits its maximum at 1. The very top of our curve exists at 1. For what value of x does that occur? Well, within that first positive rotation, my maximum occurs at 0 and at 360 degrees. What is the minimum value of cos x? Well, we get down to the bottom of cos x at a y value of negative 1. For what value of x does that occur? We found that that occurs at 180 degrees. What is the amplitude of cos x? Well, I know that my amplitude is always half my height. I go from 1 down to negative 1. That's a height of 2, so half of that is 1. And what is the period of cos x? How long does it take for that cos curve to repeat? 360 degrees is the period. There we go. So notice most of those properties are going to be the same with the exception of when do I hit my maximum and my minimum. So let's take a look then at making comparisons between our cos graph and our sine curve so that we can see some key components to it. So what I'd like you to do is just get down some key features. And if we were to go all the way down to the bottom of that page, we're going to notice a few things that are different. So I'd like you to focus on the right side of your page right now. And this is going to help us to being able to create our sine and our cos graphs very quickly. Let's look at the left side of that different column. So I'm just going to put a little wavy line down the middle. Notice if we're talking about our sine curve, I have a key difference right off the bat. My sine curve begins at the origin. My cos curve begins at 1. So our y-intercepts are different. So how can we often think about our sine curve? So let's look at the green. If you were to focus in on that process, then we can start to generate our sine curve. Where does my sine curve begin? Well, on my set of axes, I know that my sine curve begins at the origin and then rises. And if I know that it begins that way, then I can finish off my sine curve pretty quickly by saying I know I hit my peak, I know I come back, I know I hit my minimum, I know I come back. If we were to then focus in on my cos graph, well, my cos graph begins at 1. And if I was to focus in then on what happens with that sine curve, it begins at 1 and then falls. And if I know that portion, then I can finish off my cos curve. And we have two pretty functional sketches at the very beginning. The only thing that I want you to maybe focus in on a little bit is our zeros. So where does that curve end up hitting the x-axis? If we focus in on our sine curve, we know that our sine curve hits at 0 because we start there. We rise and hit our peak at 90. We come back to 0 at 180. We hit our minimum at 270. We come back to 0 at 360. My cos curve, I can construct the same way. I start at a peak at 1 and then I fall. Well, I hit my first 0 at 90, I then go to my minimum at 180, I then come up and hit my 0 at 270. Let's use the nature of those curves to come up with our key features. If we were to examine now the left side of that page, we should be able to go through and hit out all the things about those two curves that are the same. My period, how long does it take for each one of those curves to repeat? 360 degrees. What is the amplitude of each one of those curves? They each have an amplitude of 1. Why? Because they each have a maximum of 1, and they each hit a minimum at -1. What is the domain for each one of those curves? You could sub in any value for x that you wish, and we can calculate it. What is the range for each one of those? We go from -1 up to 1 in each case. So, your job now that we're done examining or investigating each one of these curves is to make sure that you could go through and put a very, very quick sketch down of a sine or a cos curve in 15-20 seconds. It's to be able to break down the key features of those graphs. So if you could do what we did on the left, produce a quick sketch of each one of those graphs with some sort of focus on when does it hit its 0, then I think you've got everything you need from our lesson today. Okay, good luck.